Welcome back to the deep dive. Today we're diving into a question that, well, it pops up surprisingly often in everyday conversations.
Mhm.
Are bigger cars truly safer in a crash?
hmm
It's a common belief, right?
hmm
Often presented as like an undeniable truth. But how do we actually test that statistically?
Yeah.
Especially when we're comparing, more than just two types of vehicles.
That's precisely the challenge. Relying on anecdotes or just a few observations can be incredibly misleading.
Right.
To really get at the truth, to rigorously determine if there are significant differences between multiple groups, we need a robust statistical framework. And for that, we turn to analysis of variance, or ANOVA.
Okay, ANOVA. Let's unpack this then. Our mission today is to take a deep dive into ANOVA, understand its core concepts, why it's so powerful, and, well, how it helps us make smarter, data-driven decisions.
Exactly.
Whether it's about car safety or even something seemingly simple like how different amounts of candy might affect restaurant tips, ANOVA gives us a clear path.
It does.
We'll start with a foundational one-way ANOVA, then build up to two-way ANOVA. By the end, you'll not only understand what those p-values and f-statistics mean, but you'll have a new lens for critically evaluating claims about differences between groups.
Hopefully, yeah.
So let's start with our car safety example. Our source material presents real crash test data, specifically focusing on the head injury criterion, or HIC.
HIC.
Think of HIC as a measurement of the probability of head injury. The higher the HIC, the greater the risk. This data is broken down by vehicle size, small, midsize, large, and SUV.
4 groups there.
Just looking at the raw numbers, small cars seem to have higher average HIC values. But the crucial question for us is that difference truly statistically significant?
And it's tempting, isn't it, to think, why not just compare each pair of car sizes using a standard 2 test? Like small versus midsize and small versus large and so on.
Yeah.
For 4 categories, that would mean, what, 6 separate comparisons?
My gut reaction would be more tests, more confidence. But I have a feeling that's, a classic statistical trap waiting to spring.
You're absolutely right to be cautious. That's a really common misconception, and it's a critical pitfall to avoid.
Okay.
If you run multiple 2-sample tests, each with, say, a 0.05 significance level, the actual overall risk of making a type I error, which is, incorrectly concluding there's a difference when there isn't one, just skyrockets.
Skyrockets, how much?
For those 6 tests, that risk could leap to over 70%.
70, wow. Imagine the consequences of falsely concluding a safety difference based on that.
Precisely. One-way ANOVA is designed exactly to avoid this problem. It lets us test if there's any significant difference among several means, all in one single controlled test.
Ah, okay. So it's about getting the big picture first, without kind of muddying the waters with all those separate tests. What at its heart is one-way ANOVA doing?
Well, at its core, one-way ANOVA is comparing the variability between your groups to the variability within those groups.
Between versus within.
Yeah, it's asking, are the average HIC values between small, midsize, large, and SUV cars different enough from each other to stand out compared to the natural variations you see within each car size category?
Makes sense.
And it's called one-way because we're looking at the effect of a single factor, in this case, just vehicle size, on our outcome, the HIC.
Gotcha. And what kind of statistical tool helps us make that comparison? I'm guessing it's not the usual normal distribution we often hear about.
Indeed. One-way ANOVA relies on the F distribution. You can think of the F statistic, which comes from this distribution, as a ratio.
A ratio.
Yeah, it's basically the variation between the sample means divided by the variation within the samples. A large F statistic suggests that the differences between your groups are much greater than the sort of random noise within them.
So a big F means the groups are really pulling apart.
That's a good way to put it. It's a powerful way to quantify if those group averages are truly different.
Okay. Before we throw our car data into this, what are the key assumptions? The ground rules we need to be aware of for one-way ANOVA.
Right, the requirements. Well, the good news is these tests are pretty robust, meaning they can often still be useful, even if conditions aren't perfectly met.
Okay.
But the main ideas are your population should be roughly normally distributed.
Roughly normal, okay.
Their variances should be fairly similar. There's some flexibility, but you don't want wildly different spreads. And your sample should be independent, not paired or matched, and randomly selective.
Right. Basic good sampling practice.
Essentially, yeah. We want to ensure we're comparing apples to apples and not introducing bias.
All right, so how do we actually run this? And maybe more importantly for most of us listening, how do we interpret the results? Because let's be honest, we're probably using software to crunch the number.
Exactly. The complex calculations are, thankfully, handled by technology. For you, the key is understanding the logic.
Okay.
First, we set up our hypotheses. The null hypothesis, H0, is always that all the population means are equal. So for our cars, mean HIC for small, mid-size, large SUV, no difference.
No difference is the null. Got it.
And the alternative hypothesis, H1, is simply that at least one of those means is different from the others. Importantly, it doesn't say which one, just that a difference exists somewhere.
Okay, just that the null isn't true.
Pretty much. Then the software gives us that F statistic we talked about, and crucially, a p-value.
The famous p-value.
The famous p-value. You can think of it as the probability of observing results as extreme or even more extreme than what we actually found, like seeing these specific HIC differences between car types, if the null hypothesis that all means are equal were actually true.
So a tiny p-value means...
What exactly? A tiny p-value means that scenario where there's no real difference in car safety, yet we somehow observe these HIC variations just by random chance, is highly unlikely.
Okay.
So if your p-value is very small, typically less than our chosen significance level, which is often 0.05,
0.05, yeah.
then you have strong evidence to reject the null hypothesis. You conclude there is a significant difference somewhere among those means.
And if the p-value is bigger than 0.05.
Then you don't have enough evidence to reject the null. You say you failed to reject it, meaning you can't claim a significant difference based on your data.
Okay, fail to reject, not accept the null.
Exactly. It's a subtle but important distinction. We never prove the null is true, we just might lack evidence against it.
Got it. Let's apply this to our car crash HIC data then. The average HIC values were small, 290.0, midsize, 180.8, large, 172.6, and SUV, 176.8. Our source tells us that with a 0.05 significance level, the ANOVA produced an F statistic of 7.6853 and a p-value of 0.000.
0.000. Okay.
So that's our conclusion.
Well, given that p-value of 0.0000, which is dramatically less than our 0.05 cutoff, we confidently reject the null hypothesis. This means there's compelling evidence to conclude that the mean HIC values for these four vehicle size categories are not all equal. There's a statistically significant difference in head injury measurements related to vehicle size.
That's a significant finding. And it sort of validates that initial informal observation we had.
It does.
But here's the next logical step. If ANOVA tells us that there's a difference somewhere, does it tell us where that difference is? Like, is it just the small cars being different, or is it maybe midsize versus SUV, or what?
That's a critical point, and yeah, another common trap. ANOVA itself only tells you that at least one mean is different from the others.
Okay.
It doesn't pinpoint which specific group or groups are responsible for that difference. It's like a smoke detector. It tells you there's a fire somewhere in the building, but not which room it's in.
Good analogy. So how do we find the source of the fire, so to speak? How do we pinpoint the specific differences?
That's where post hoc tests come in. Post hoc just means after this.
After the ANOVA.
Exactly. After you've established an overall difference with ANOVA, you use these follow-up tests to make specific pairwise comparisons, like small versus midsize, small versus large, but crucially, while still controlling to that increased risk of type I errors we discussed earlier.
Okay, so they fixed that multiple comparison problem.
They aim to, yes. Our source highlights one common and robust method, the Bonferroni multiple comparison test.
Bonferroni? What's special about that one? Why is it like a go-to here?
Well, the Bonferroni test allows us to compare every possible pair of groups. So in our case, small versus midsize, small versus large, small versus SUV, midsize versus large, and so on. All 6 pairs.
Right.
But it does something critical. It adjusts either the p-value for each individual comparison or, more commonly, it adjusts the significance level you use for each test. It makes it harder to declare any single comparison significant.
It makes the hurdle higher for each pair.
Precisely. This adjustment ensures that the overall probability of making even one type I error across all your comparisons remains at your desired level, usually that 0.05.
So it keeps the overall error rate in check.
Exactly. It's not just, a mathematical tweak. It's what allows us to say with more confidence, yes, statistically, this specific group is different from that specific group without accidentally crying wolf too often.
Right. It gives credibility to pinpointing the difference.
It does. It's the difference between maybe a misleading headline and actual actionable safety data.
Okay, so it sounds like we're being extra cautious, which is good. Let's apply Bonferroni to our car HIC data. With 4 car sizes, we said there are 6 possible pairings. What did the Bonferroni results reveal?
Our source shows that for the comparison between small and mid-sized cars, the adjusted p-value was 0.003.
0.003, still less than 0.05.
Definitely. So we reject that specific null hypothesis, concluding there's a significant difference between small and mid-sized cars, HIC means.
Okay, what about others?
Similarly, Bonferroni also showed significant differences between small and large cars. The p-value there was 0.0001 and between small and SUVs with a p-value of 0.002.
Wow, so small cars are different from midsize, large, and SUVs.
That's what the test indicates.
Here's where it gets truly impactful then. The Bonferroni test seemed to pinpoint that the mean HIC for small cars is significantly different from all the other categories.
Mm.
And interestingly, did it find any differences between, say, midsize and large, or large and SUV?
According to the source, no. None of the other three categories, midsize, large, and SUV, showed significant differences among themselves after the Bonferroni adjustment.
So the significant finding really revolves around the small cars.
It appears so. But this aligns perfectly with our initial informal observation, but gives it strong statistical backing. Small cars are indeed associated with significantly higher head injury measurements in this dataset.
That makes perfect sense. So one-way ANOVA gives us the overall picture, is there any fire? And then tests like Bonferroni help us zoom in, finding which room the fire is actually in.
Exactly. It's about knowing if a door is open and then finding out which door is open. A two-step process.
Okay, that makes perfect sense. We've cracked the code on single-factor comparisons, but, the world isn't always so simple, is it?
Rarely.
What if two different things are influencing our data and maybe even interacting with each other? Like you mentioned earlier, say, crash forces on femurs. It might matter not just what size car it is, but also which leg left or right is being measured.
You've hit on the next level of analysis. Two-way analysis of variance.
Two-way ANOVA, okay.
This is the tool we use when our data are categorized by two different factors simultaneously. So factor 1 might be vehicle size, and factor 2 might be femur side.
And what's the big advantage here? Can't we just do two separate one-way ANOVAs?
But the fascinating part here is that two-way ANOVA doesn't just look at the individual effect of each factor in isolation. It also allows us to test for something called an interaction between them.
Interaction.
This is something a simple combination of one-way ANOVAs would completely miss.
An interaction. What does that actually mean in a practical sense, like with our car crash data?
Think of an interaction like a synergy or maybe a clash. There's an interaction between two factors if the effect of one factor changes depending on the level or category of the other factor.
Okay, so the effect isn't consistent.
Exactly. For example, if the difference in femur force between small and large cars was much bigger for left legs than it was for right legs, that would indicate an interaction. The effect of vehicle size depends on which femur side you're looking at.
Ah, I see. Like maybe one drug works better for men than women, even at the same dose?
That's a classic example of an interaction, yes. The effect of the drug depends on the gender category.
Okay. Our source uses femur impact data from crash tests, categorized by femur side, left to right, and vehicle size category, small, midsize, large, SUV. How might we visualize if an interaction is present before even running the numbers? Is there a way to get a feel for it?
Yeah, we often use something called an interaction graph. You'd plot the average femur force for each car size, but you'd have separate lines on the graph, one for left femurs and one for right femurs.
Okay, two lines.
Right. If those two lines are roughly parallel across the different car sizes.
Like train tracks.
Kind of like train tracks, yeah. That suggests there's probably no significant interaction effect. The pattern of femur force across car sizes is similar for both left and right legs.
And if they're not parallel? If they cross or spread apart?
If the lines cross or if they diverge significantly going in different directions, that's a strong visual cue that an interaction might be at play. The effect of one factor seems to change across the levels of the other. For the femur data in our source, the graph showed lines that were actually mostly parallel.
Okay, suggesting maybe no interaction there. What about the requirements for two-way ANOVA? Similar to one-way, but with maybe an added twist for the two factors.
Yes, the core requirements are very similar. Approximate normality within each combination, similar variances, and independent random samples. The key addition for two-way ANOVA, and it's important, is needing a balanced design.
Balanced design, what's that?
It just means that each cell, each combination of the two factors, like left femur in a small car or right femur in a large car, must have the same number of sample values.
Ah, equal sample sizes in every little box.
Exactly. It ensures the analysis is equally powered across all the different combinations and simplifies the calculations, though technology can sometimes handle unbalanced designs too.
Okay. And the procedure for analyzing it, is it just finding one p-value again, or is it more complex?
There's a critical sequence you absolutely must follow. Think of it like a specific workflow or a decision tree.
Okay, what's step one?
Step one. First and foremost, you always test for an interaction effect. Your null hypothesis here is that there is no interaction between the two factors.
Test interaction first. Got it.
If the p-value for that interaction test is small, say less than or equal to 0.05, you reject that null. You conclude there is a significant interaction, and if you find an interaction, you stop there regarding the main effects.
Stop. Why stop if you found something interesting? That still feels a little counterintuitive.
It's because if a significant interaction exists, it means the effect of one factor is dependent on the level of the other factor.
Right, like the drug effect depending on gender.
Exactly. So it no longer makes sense to talk about a general effective vehicle size overall or a general effective femur size overall if those effects change depending on the combination. The interaction itself becomes the most important finding. Your interpretation has to focus on describing that specific interplay rather than looking at the factors in isolation.
Ah, okay. The interaction is the main story then, so you don't look for the separate effects if they're tangled up together.
Precisely. Now, what if you don't find an interaction?
Okay, so if the key value for interaction is large, say greater than 0.05.
Right. In that case, you fail to reject the null of no interaction. You conclude there's no significant interaction effect. Only then do you proceed to step two.
And step two is?
Step two is testing for the individual main effects. You test if there's a significant effect from the row factor, like femur side, on its own, and you test if there's a significant effect from the column factor, like vehicle size, on its own. For each of these, you look at their respective p-values.
Okay, so interaction first. If yes, stop and interpret interaction. If no, then check main effects.
That's the crucial workflow.
Let's look at our femur craft test example again then. Our source provides the results from the software. What did we find following this workflow?
Okay, so first, the interaction. For the interaction effect between femur side and vehicle size, the p-value reported was 0.763.
0.763, that's pretty big. Much larger than 0.05.
Much larger. So we fail to reject the null hypothesis of no interaction. We conclude there is no statistically significant interaction effect here. The way vehicle size impacts femur force seems generally consistent, whether it's the left or right leg, and vice versa.
Okay, no interaction. So we proceed to the main effects.
Exactly. So next we look at the row factor, which was femur side. The p-value for the main effect of femur side was 0.3498.
0.3498. Still greater than 0.05.
Right. So again, we fail to reject the null hypothesis for this factor. There's no significant overall effect detected just based on which femur side is being measured.
Okay, and the last one, the column factor, vehicle size.
For the column factor vehicle size category, the p-value was 1.7343.
0.7343. Also much greater than 0.05.
Correct. So we fail to reject the null for this man effect as well. There's no significant overall effect found from the vehicle size category on femur crash force measurements in this particular data set.
Wow. So for the femur crash test data, the 2A ANOVA indicates that the crash force measurements are not significantly affected by any interaction between side and size, nor by which femur side it is alone, nor by the vehicle size category alone.
That's what this specific analysis suggests, yes.
That's a starkly different conclusion from the HIC data for head injuries, where vehicle size mattered a lot, particularly for small cars.
It is, and what's truly fascinating here, I think, is how applying the correct statistical method one way for HIC, two way for femur, reveals very different insights, even with seemingly similar car crash data sets.
Yeah.
It really underscores why understanding these concepts isn't just, academic busy work. It's vital for accurate real-world analysis and drawing sound conclusions. It stops us from just generalizing based on intuition or incomplete comparisons.
Wow, okay. What a deep dive into ANOVA that was. We've really unpacked how one-way ANOVA helps us compare 3 or more group means, and crucially why it's better than just doing lots of t-tests because of that inflated type I error risk.
Avoiding those false alarms.
And then we climbed up to 2A ANOVA, where we learned about the absolutely critical concept of interaction and why you have to test for that first, because it can completely change the story your data is trying to tell you.
That's right. We saw how this kind of analysis can reveal whether vehicle size impacts head injury differently across categories, or maybe if femur side and vehicle size truly affect crash forces independently, or if they work together in some way.
Right.
Knowing when to use each method, one way versus two way, and how to correctly interpret the results, especially that interaction test, that's really key to making well informed decisions from data. Doesn't matter if you're a student, a researcher, or just someone trying to make sense of a claim you read online.
So what does this all mean for you listening right now? Well, next time you hear a broad claim about how different groups compare, maybe it's about a new diet versus an old one, or different teaching methods, or,
Mm.
yeah, even how much candy affects restaurant tips,
Ha, right.
you now have the tools to ask, okay, how was that comparison actually made? Was it rigorous enough, like using ANOVA, to avoid just finding differences by chance? And if there were multiple factors involved, like age and diet, was the interaction considered?
It really does open up a whole new way of critically evaluating information, doesn't it? Seeing beyond the surface claim to the statistical story underneath.
Absolutely. And that's what being truly well-informed is all about.
Yeah.
Questioning, analyzing, and understanding the deeper statistical currents that, well, that shape our world.
Well said.
Thank you so much for joining us on this deep dive. We really hope you gained some powerful new insights today. A warm thank you from the Last Minute Lecture team.